In this video, I'll talk about the nature of a proof, two notions of entailment, and what the deductive apparatus is for the language of propositional logic. So first, it's helpful to think a little bit about when we talk about good arguments and bad arguments. Sometimes we say that a good argument is one where the conclusion, some formula that we're arguing for, some proposition we're arguing for, we say that this formula or proposition is entailed by a set of premises or reasons that we have for that particular conclusion. But this notion of entailment, where when we say a conclusion is entailed by a set of premises, is a little bit ambiguous. So we want to parse this out a little bit. A set of well-formed formulas can be said to entail another well-formed formula in one of two different ways. The first is semantic entailment. We say a well-formed formula is semantically entailed. A conclusion is semantically entailed by a set of well-formed formulas if and only if there's no way to interpret the premises in the conclusion that would make the premises true and the conclusion false. The basic idea here is that if we go about taking the smaller sentences or formulas that compose these well-formed formulas, which may be complex, if we go about assigning truth values to these smaller formulas, there's no way we can make the assignment of true and false to these smaller formulas that would make all of the premises true and the conclusion false. This notion of semantic entailment is tied up with, there's ways to kind of check this for propositional logic with truth tables and truth trees, and this is covered in an earlier video. The key thing here, though, is just to realize that there is a notion of semantic entailment, which is simply put, there's no way for the premises to be true and the conclusion false. So if the premises are true, then the conclusion is also true. A well-formed formula is syntactically entailed. Here's another different sense of entailment by a set of well-formed formulas if there's a proof or derivation of that well-formed formula. This notion of a syntactic entailment is sometimes called proof-theoretic entailment. So what we're going to explore here is this notion of syntactic entailment. So to get a clear sense of the notion, we're going to need to clarify a couple additional concepts. The first is the notion of a derivation or proof, and the second is the notion of a deductive apparatus, or the various rules that take us forward in steps in a proof. Once we clarify these notions, we'll go back to this notion of syntactic entailment when we say that a formula is syntactically entailed by a set of formulas, and we'll be able to get a clear sense of what this means. So we say a derivation of a particular formula, let's call it Q. All a derivation or proof is a finite, so not an infinite, string of well-formed formulas. So it's one formula, one formula, one formula, one formula, just a kind of list or sequence of well-formed formulas from another set of formulas, which we'll call gamma, where the last formula in this sort of sequence or string of formulas is Q, and each of the formulas in this string of formulas is a premise, assumption, or is the result of preceding formulas and the deductive apparatus. So let's take a look at what this kind of means here. Let's break this definition down a little bit. So when we talk about what a derivation is or what a proof is, the first thing is we're just saying that it's a string of well-formed formulas. It's nothing more and nothing less. But this string of formulas needs to meet certain conditions. The first condition is that the last well-formed formula in the string is the formula that is being proved, or aka, in the conclusion. So if we say we have a proof of Q, then we have a string of formulas where the last formula in the string is Q. The second condition is that every well-formed formula has to be justified in a way. It has to have, if it's in that string of formulas, it needs to either be a premise, so it's something that we just take to be true, it needs to be an assumption, something that we're just going to assume to be the case, or that well-formed formula is proved, it's sort of justified or is legitimized in virtue of the deductive apparatus. Now, we haven't talked about the deductive apparatus, and we'll make that clear in a moment, but the key thing here is that the deductive apparatus, it allows for certain formulas to be in the string. So what is this deductive apparatus? The deductive apparatus for the language of propositional logic is just a set of rules of inference, rules of reasoning, or we might call derivation rules. They're just abstract, highly general rules that allow us to write down certain formulas in a proof. There are rules, you can think of them as rules of reasoning. They allow us to take certain formulas that we already have and move to new or different formulas in the proof. In order to kind of abbreviate this list of rules, we'll abbreviate it as PD. So it's helpful to get a kind of more intuitive notion of the deductive apparatus, and we can think about this in terms of everyday life. So let's take two people, Tech and Liz, and we'll just assume that Tech and Liz, they agree about a bunch of stuff. They have similar life experiences, they agree upon the results of similar scientific studies, they have similar values, so we can sort of abbreviate all the things they accept as true in terms of gamma. And all gamma is just a list of formulas, sentences, or propositions that kind of express the things that they accept as truth. Now, we can think, though, about Tech and Liz disagreeing a little bit about what follows from gamma. We can suppose that Tech says, if gamma is the case, then propositions P, Q, and R follow. They're entailed by gamma. You should accept them as well. But in contrast, Liz might say, no, I don't really see that. You say that P, Q, and R follow from gamma or are entailed by gamma, but I don't really see how that's the case. One thing to note here is that Tech and Liz, they aren't disagreeing about the facts of the world. Remember, they have the same experiences, they accept the results of scientific studies, they agree upon the facts. What they disagree about is whether or not P, Q, and R, these letters right here that are just expressing proposition or states of affair that can be true or false, what they're disagreeing is whether or not it follows from gamma. So they might say, okay, well, we just have this vague notion of what follows from what. We might try to make this a little bit more explicit. We're going to kind of fix this problem and get to the bottom of whether or not P, Q, and R follow from gamma. So what they might do is say, okay, let's come up with a list of rules that start from gamma, start from those premises, start from these facts that we accept to be the case. And this list of rules allow us to kind of move from gamma to reason to other formulas, other propositions, other things that we accept to be true. And so all the deductive apparatus is, in general, the general idea is just a really highly general, abstract way of formulating the rules that allow you to move from one set of propositions, one set of formulas, to another set of formulas. Okay, so we talked a little bit about what a proof is. It's just kind of string of formulas that meet certain conditions. We talked a little bit about the deductive apparatus. Now we're going to kind of return to this notion of syntactic entailment that we talked about at the beginning. So a syntactic consequence or a syntactic entailment is the following. To put it one way, we can say that a formula Q is a syntactic consequence or is syntactically entailed from a set of or by a set of formulas gamma in the language of propositional logic if and only if there's a derivation or proof using the deductive apparatus PD of Q from gamma. So the idea here, there's this sort of short and sweet of it is we can say that Q is syntactically entailed by a set of formulas gamma if and only if you can use this list of rules that we kind of talked about to move from gamma all the way to Q. You can kind of reason from gamma using the rules that we lay out to Q. To kind of put this, to show that Q is a syntactic consequence of gamma, we'll write gamma, the single turnstile Q. And all that says is gamma syntactically entails Q, or there's a proof such that we can move from gamma all the way to Q. Let's look at a more concrete or a little bit slightly more fleshed out example. We might write PMR single turnstile Q. And all that's being said here is that Q is a syntactic consequence of P, M, and R. In short, that there's a proof that begins with P, M, and R. These are the premises that we accept to be the case and ends with Q.